I'm going to go over a general overview. I don't have example problems to solve today, but I'm going to set up a lot of the calculations and then walk us through how we may solve them, because we've done a lot of examples in class, in the homework. Does anyone feel like the problems are getting redundant? Or do they all feel novel and challenging? Novel and challenging, okay. Well, by the end of the semester, we want you to feel like they're all getting a little bit redundant, and then we'll have done our jobs. So we still have a couple weeks. So I think the project part 2 will really help lock in the energy balances, because you'll have to do a lot of energy balances on sort of the same process. So I don't think I'll have a full 50 minutes of overview, so we'll have time for questions. We'll start off with questions about the exam, and then if we have time after that, we can talk about the project a little bit. All right, sound fair? So jump in with any questions. So let's start off with the energy balance. So actually, let me give a bigger overview. There are 2 steps or 2 concepts that we have to invoke to solve these energy balance calculations. The first one is the energy balance. The second is state changes. So these would be delta H, delta U, and so on and so forth. And when you go into thermodynamics 2, you'll be looking at delta Gs, right? Changes in fugacity, which is this term that confuses everyone, right? This information here is accounting. Right? Don't lose energy. Right? This is just the preservation of the law of conservation of energy, otherwise known as the first law of thermodynamics. Don't lose energy. That's the first part. The second part relates to material properties, temperature, pressure changes. So for a given material, how much energy, how much enthalpy does it take to change the state from state 1 to state 2? Now recall, in thermodynamics, we like to refer to things as states because we don't actually care how we get there. A state is a collection of variables that is sufficient to describe the properties of the system. So for a single component, single phase system, that number is 2. Right? So in thermodynamics, the fundamental units that we derive everything from are the relationships between specific volume or density of the material, the entropy, and the internal energy. So we have the first law of thermodynamics, the second law of thermodynamics, and that matter exists in real 3D space. Those are the only principles that define the starting point of thermodynamics. Everything else that we do is a manipulation of these variables. So we'd like to translate these into units that are a little bit more convenient to work with. And as a group scientific culture, we have determined that P, V, and T are the units to convert into. So what we do is we relate all of the equations, the first law and second law of thermodynamics, and we create new variables in order to make them things that we can more easily measure. So the Gibbs phase rule, the starting point, assumes that if I have 2 variables, I should be able to work out an equation to calculate the third. So that's why a state is a collection of sufficient number of variables that fully define the state. So in our purposes, that's generally the temperature and pressure. But it doesn't always have to be the case. It could be the temperature and the specific volume to determine the pressure. Right? These can be manipulated in multiple different ways. But everything we focused on was given a pressure and temperature, then an equation of state, let's say like the ideal gas law, right? PV equals RT. If I have pressure and temperature, I can calculate the specific volume. Now what we need to remember is that if we have this information, that is equivalent to saying that we have this information. that we can perform an energy balance, an entropy balance, and, well, the volume connects the dots between the two of these. Does that make sense? So, energy balance, don't lose energy. State change, how much energy does it take to change a fluid from one state to a different state? That could involve phase changes, it could involve temperature changes, it could involve pressure changes, it could involve chemical reactions. We are changing the configuration of the system. We are changing the energy that it's stored. So every time you approach one of these problems, you will have to do both of these steps in order to answer the question in units that we care about. So you could perform an energy balance, but then your units are always going to be in units of enthalpy, units of internal energy. And I cannot visualize internal energy and enthalpy units particularly well. So if you want to convert the energy balance into things like temperature and pressure, you have to use state changes. So steam tables, what do those fall into? Are they energy balances or state changes? The steam tables. State changes. C sub P delta T, energy balance or state change? State changes, right? So you have to combine these two. If you do not combine these two, you will not be able to answer any of the questions. Okay. So every time you start off with an energy balance, then you have to involve state changes at some point. So remember that when you're working through your problems. First, write the energy balance, determine which enthalpies you need, then introduce equations for the state changes in order for you to compare that to different temperature and pressure inlet and outlet conditions. There's a question here.
So when we're like setting up an energy balance or something, we have like Q equals like some delta of sorts. Is it best to go with like delta H? Because then if the true equation was delta U, the terms will like just cancel out, or some terms will go to zero and give us delta U.
Let's go over that. That was the next step, is talking about the energy balance. So for the energy balance, number one, okay. There are no deltas in this expression here. Where do the deltas come from? Yes?
We can just make them kind of like rearrange stuff.
We can rearrange the in and out into a delta form. That's one way where a delta can come from. And then that lends us to the state changes, right? Where we can say that the rate of change of enthalpy is the rate of change of internal energy plus the rate of change of the PV. We can also write that dH is equal to the integral of C sub P dt, and that is because this heat capacity is defined as how does the enthalpy change as a function of temperature at constant pressure. Right? So this is not some sort of fancy mystic art. This is literally just someone said, you know what? This would be a good variable to measure. I don't know how to predict it, but if I can measure it, then I can use this system in order to calculate these more complicated problems. Okay, there's one other way that I can get a delta out of this equation. How can I do it? So yes, we can manipulate these enthalpies to get us delta H's, which we can relate to C sub P dT's. What's another way I can get a delta out of this?
You're approximating the derivative.
Exactly. I'm actually approximating. It's exactly the right answer. So I can integrate du dt from time 1 to time 2, or state 1 to state 2. We don't care how long it takes to do that. And that gives me a delta u. u2 minus u1, final minus initial. Right? So we can manipulate to get this to a delta u in some simplified situations for enthalpy. We can manipulate this by integrating it, and that gives us exactly the delta u. So let's talk about a closed, constant pressure system. Take a second, write down what you think the energy balance for a closed constant pressure system is. You can either do it in the differential form, before we integrate it, or you can do it in the integral form after we integrate it. It's up to you. Sorry, not close. We'll do constant pressure first. Well, start working on that one. The easier one is constant volume. I meant to do constant volume. We're going to do constant pressure next, but it'll transition us into making it a little bit easier in terms of the flow. Okay, so I'm going to write out the differential form. du dt is equal to q dot plus w. And let's write it out in the integral form. So we just integrate this expression, and again, thermodynamic integration is very fun, should be very non-stressful. If I see a du, I just turn that into a delta u. Quite straightforward. So then this is going to be delta u, which is equal to u of the system in the final state minus u of the system in the initial state, is equal to not q dot, but the total amount of q in and out and the total amount of work in and out. So that's my energy balance. So if I wanted to relate this to a temperature and pressure that we are interested in, I need a state change. What is the state change that seems to fit nicely within this expression here? I don't have it on the board, but I have a close brother or sister to it on the board.
C sub v.
C sub v is equal to what?
Delta u.
So C sub v is defined as the change in the internal energy as a function of temperature while holding the volume constant. Again, this is not some mystic dark art. This is a value that people decided, you know what, this might be a good thing to calculate because I can't determine it from my thermodynamic theory, but if I can measure it in the lab, then I can pretty easily unpack it. So what we can do then is rearrange this expression, right? Basically perform a separation of variables, move the dt to this side, integrate both sides of the expression, and I get that the delta u is also equal to the integral from T1 to T2 C sub v dt. I have now combined an energy balance with a state change, and that allows me to get access to the temperatures and the material properties of the system. So if I were to heat up benzene in a closed constant volume system versus heating up water in a closed constant volume system from the same temperature to the same temperature, what is the only thing that changes in my calculation here? The only thing that changes is C sub v, just the material properties of the system. So I have taken all the complexity of all of the quantum mechanics and all the physics and all the statistical mechanics and all the different bonds and the hydrogen bonds versus everything, and I've turned it into one number. Now, if you don't think that's powerful, you haven't done enough thermodynamic calculations, right? Because if I look at benzene and I look at water, I don't see the same compound. Their reactivity is completely different. Their phase behavior is completely different, right? Their carcinogenic nature is completely different. But in thermodynamics, the only thing I care about is what is its heat capacity as a function of temperature. So thermodynamics takes vast complexity of the universe and simplifies it down to one measurement that we want to make, right? Okay. So let's do now the closed constant pressure system. All right? Write it out in the differential form, write it out in the integral form. This one involves a little bit of a trick, but it's not too drastic of a trick, and it's something we've seen before in this class. see some pens working, some pens not working. We get du dt plus p dv dt, which is equal to dh is equal to q plus w. So then I can write this out in the integral form. Delta H is the enthalpy at state 2 minus the enthalpy at state 1 is equal to the total amount of Q plus the total amount of W. Now we need to pair this up with a state change because I don't see any temperatures and pressures in this equation. So then I can write that delta H is equal to the integral from T1. Actually, I'll write this from state 1 to state 2. Oops. State 1 to state 2, C sub p dt and this is because the pressure is constant. If the pressure were not constant, we'd have to add in the dPV as well. Okay, closed systems. Feel good about closed systems? Question back here. Vernon.
The reason you went from, because like first we were solving, we want to know what the UDT is, right? Just
On this one here, you mean?
because like our general energy constant.
Yes, this one here.
I always thought of like PdVdt as like work.
Yes, this is PV work. So the convention here in a lot of thermodynamics is like the work term is some fancy complicated process like a turbine or a compressor, something that has really complicated mechanics. The PV term there, that's just the whole system getting bigger or smaller. So for example, I could be extracting work out of a process at a constant volume. So that would be the case if I had like a turbine for power generation. The walls of the turbine aren't expanding and contracting, but through some clever mechanism of how they carefully expand the gas over blades, that would be getting mechanical work out of the system. So this is like blowing up a balloon or changing the size of a piston cylinder device. So this is the PV expansion work, and this is going to be some sort of shaft work, some sort of other more complicated process. It could be an impeller spinning and sort of dissipating heat energy by friction. That's another way that could be. Okay. Question?
Have constant volume or pressure, could we still calculate that by like doing the integral of CV dt plus the integral of CV dt?
That's a very good question. So the question is, what if we had constant pressure and constant volume? What would happen to our thermodynamics?
T is defined.
T's fixed.
Oh, but what if neither of those were constant?
You cannot change the state by having both of those be the same. So that's what this relationship of noting that three variables define all of the properties of the system. Right? So if you keep the pressure and the volume constant for a single component, single phase, you cannot change the state. You cannot vary the temperature. And the second law of thermodynamics, as an aside, if you guys are really curious about this, right? If we look at an isotherm, so that's pressure versus volume, right? It always has to look like this. So this is like the ideal gas law. So right, you have P is equal to RT over V. That's a radical function, right? So if I look at this at a constant temperature, so the rate of change of the temperature dt is 0, so this is called an isotherm. So how much does the pressure change as I compress a fluid? This is what we use to tune our fancy equations of state to get our properties. The slope of this line must always be negative. So that tells us that dP dV at a constant temperature must always be less than 0. If this is ever violated, that means that you are creating entropy out of nothing. Sorry, you're removing entropy out of nothing, and you violated the second law of thermodynamics. So a consequence of the second law of thermodynamics is that this must always hold true. So if I don't change the pressure or the volume, that means my temperature cannot change either. So you cannot change those. That's a process that is not possible. So you can't keep the volume and the pressure the same and have the state change. Yes?
And trying to like change both of those at the same time.
You could change both of them at the same time, but it would be unpleasant. So what you would want to do is change First, let's say the volume, then change the pressure. You would break it into 2 steps.
Oh, okay, and that would end up being the same. Like,
Correct. It would be the same. So you could, but you'd have to do like a double integral, right? So instead you want to do it isobaric, then changing the volume. Or sorry, change the volume, then change the pressure. So that's what you would want to do. You'd want to break it into 2 stages. There's a question over here somewhere? Okay. All right? Do you guys all feel like thermodynamics experts now? Almost? Getting there? Okay, let's do open systems. So let's do an open, steady state system. Open, steady state system. Let's write this one out. Okay. 0 is equal to the summation of the flow rates in minus the flow rates and enthalpy out plus the heat plus the work. Now, if I want to, I can move the in minus out to the other side of the equation, and we get out minus in is equal to Q plus W. Now, in the Felder textbook, it's always Q minus W. That's because they define work as being positive out of the system. In this balance here, I have defined work as being positive in the system. How do I know that I defined work as positive going into the system? Yes?
Don't you just say that it is?
But what about mathematically? Do I write something mathematically that tells me that I have defined work as being positive into the system? So let's look at my general balance equation right here. So what I am doing is I'm asking you, what is the amount of money in your bank account and how does it change? What is the rate of change of the money in your bank account? Okay? And these are all the different part-time jobs that you have. Okay? So if I have work, I have 10 work dollars. Does my bank account increase and have a positive slope, or does it decrease and have a negative slope? Increases because I'm adding it. It's as simple as that. On this equation, all I'm doing is saying, how much money do I have in my bank? How much is the rate money of my bank account changing as a function of time? If it has a positive slope, it's going up. If it has a negative slope, it's going down. So if I have nothing else going on, but I give it $10 of work, my bank account balance is going up. Right? So that's how you know what my convention is just based on the balance. Right? I'm putting money in, I am taking money out, and here I'm defining these as positive going into the system just because it's a plus sign. Right? So it's as simple as that. How much does the total balance of energy change? And I'm adding and subtracting a bunch of stuff. Right? The reason why our energy balance looks this way is just based on convention. If this were an electrochemistry class, this balance would look different. If this was a civil engineering class, this balance may look different. If this were a global warming class, this balance may look different. Right? It just depends on what's the convention of how you write the energy and which energy sources you want to consider. Right? So we're not considering radiative energy coming from the sun. If you wanted to, just add it into the balance. Right? Simple as that. So whatever you want to do, you can add it in there. Okay. So this is our open steady state system. Does this apply to phase change systems? Does it apply to phase change systems? Yes. Does it apply to reacting systems? Does it apply to systems that don't change phase? Does this apply to ideal mixing? Does this apply to non-ideal mixing? Applies to everything, right? I've made no assumptions on this. I'm just keeping track of my energy. So let's say I did have non-ideal mixing. What would I have to do, right? I was mixing sulfuric acid and water. What do I need to do? Do I need to combine it with a state change? Yes?
Wouldn't it just be included in the HI of the outlet stream, so it just change the enthalpy of whatever's leaving the system?
Correct. So if I choose a particular reference state, the state changes tell me what numbers that I should put into here and how they relate to temperature and pressure and how those relate to the material properties that we're looking at. So when I mix sulfuric acid and water, that's changing the state. Changing the composition is changing the state of the system, right? If I mix two gases together, do you guys remember the delta H, delta S of mixing equation? Negative summation xi ln of xi, right? I am generating entropy when I do a mixing process. That changes the state, right? If I'm changing the entropy, well, I'm certainly changing the state of the system, right? So changing temperature, pressure, changing composition, those are all differences in state. Changing the phase, difference in state, okay? So the only difference between a reacting system, a non-reacting system, a single phase, a multi-phase, an ideal mixing, and a non-ideal mixing is nothing to do with this equation. Works perfectly good for all of them, okay? The only difference is which state changes do I consider? Okay, so we're going to talk now about state changes. So let's look at internal energy changes. So for temperature, delta U, C sub V dt integrated from T1 to T2. So I'm hopefully going to try and organize all of the assumptions in one place. And then, of course, if we assume that the heat capacity is constant, this is just C sub V delta T. If heat capacity is not constant, then we have to use a correlation for the heat capacity. We can take the heat capacity correlations for C sub P if they're an ideal gas and just minus R. But I'm trying to write down all these assumptions, so don't stress too much about that. So for pressure changes, for pressure changes, we're going to say that delta U is always going to be equal to 0. We're not going to be considering the changes in internal energy. So for ideal gases, this is 100% true. For liquids, it's kind of true, right? The short answer is that to calculate delta U for a liquid at pressure changes is kind of super hard, like super, super hard. So temperature changes, integral C sub V dt. Pressure changes, delta U 0. So we'll make it easy there. Okay, so for enthalpy changes, for temperature, delta H is the integral from T1 to T2, C sub P dt. Now recall, C sub V and C sub P, these are dependent upon the phase. For pressure changes, for gases, delta H is 0. This is only true if you have an ideal gas, but this is the calculation that you'll spend some time on in your thermodynamics 2 class. This is tractable because our equations of state, right? Equations of state relate between pressure, temperature, and volume are actually pretty good for gas state. They're pretty good. So we'll teach you the thermodynamics necessary to calculate what is the change in enthalpy as a function of pressure for a non-real fluid using an equation of state like the Peng-Robinson equation of state. It's pretty good, actually. Peng-Robinson equation of state, not good for liquid properties. Okay, so for liquids, delta H is equal to delta PV. Nothing but underbars here, hats. Just make sure you're putting the right units in, if it's per mole or not. Generally, we're going to assume that the volume of the material is constant. We're going to assume it's incompressible. So that'll mean we can pull it out of the integral. It'll be V delta P. And then the only other things that we had to add on to here, I'll call this additional delta H's. We have delta H of vaporization. That's going to be a function of temperature, something you can look up. We can have delta H of mixing if we have a non-ideal fluid. This is going to be a function of temperature and the composition of the system. Yes?
Wouldn't pressure changes be more significant in a gas than a liquid?
So
The change in enthalpy?
So the enthalpy changes are sort of lumped into it already. But as it turns out, if you substitute the ideal gas law into the true thermodynamic function for what dH is equal to, the pressure dependence goes away. Because the assumption of an ideal gas is such that no molecule ever sees any other molecule. So conceptually, if I squeeze those molecules closer and closer together, they still don't see each other. So there should be no sort of physical dependence upon the pressure there. But the PV expansion is important for the enthalpy for gases, but it's already included in the terms. So that's why we define U plus PV. So that PV is important, but that's why we made this new variable called the enthalpy.
So I haven't taken a look at practice example yet, but I heard about the banana to balloon problem.
That is energy balance, not necessarily state change.
Okay.
So I'm not asking you for the change in state of the gas. I'm asking you for the physical PV expansion of that problem. For the infamous banana problem. Okay, so additional delta H's that we have. Heat of vaporization. This varies as a function of temperature, but you could equally consider this varying as a function of pressure as well, right? Because if I have saturated steam, I could tell you it's at 1 atmosphere pressure. What temperature is it at? Saturated steam at 1 atmosphere pressure, what temperature is it at? 100 degrees. Saturated steam at 100 degrees C, what pressure is it at? 1 atmosphere, right? So you can think of the heat of vaporization as being a function of temperature or as a function of pressure. It's up to you. They're equivalent. We generally like to think of things in terms of pressure. Mixing, so if I mix sulfuric acid and water, what is the change in enthalpy? It depends on the temperature of the system, because why not? Everything depends on the temperature of the system, right? Because it's a thermodynamic variable. The thing you have to remember with thermodynamics, if I change one thing, I change everything. Okay? So if I change the temperature and I don't explicitly hold another variable constant, I could very well change the specific volume, I could very well change the pressure, and I would change potentially internal energy and entropy and all those, right? So if I change one variable in thermodynamics, I change all the other variables all at the same time. So of course, delta H of mixing is going to be a function of temperature. It's also going to be a function of pressure as well, but we kind of neglect it because liquids aren't particularly sensitive to changes in pressure. But technically speaking, all of these are a function of all other variables. But we just sort of list the ones that are the most important. And the last one we talked about was the delta H of the reaction, which is going to be a function of temperature as well. So in your homework, you should have calculated, right? I have a reaction occurring at 100 degrees Celsius. It's isothermal. And then at the end of the question, I don't ask you what's the heat in and out of the system. Well, that'd be far too simple, right? Because you all know how to use the open energy balance. I ask you instead, what is the heat of reaction at 100 degrees C? Do you guys remember that in the homework? Vaguely? That's because the Q is equal to the delta H of the reaction, right? But I'm trying to force the concepts of what these equations mean, not asking for rote reproduction of specific variables, right? I want you to know why the equation communicates the specific information, not your ability to perform the mathematics. I know that you can all do the math, right? So for example, if I said, here's the bubble point equation, tell me the bubble point at x equals 0.2, right? Everyone would get it 100%. But if I say, what is the minimum pressure of the two-phase region that I can operate a flash separator at, it's asking exactly the same question. I might have it backwards. It might be the maximum pressure. But the idea holds there, right? I'm asking you for the concept to translate the real-world challenges to the actual mathematics, right? That's the information I'm trying to get across in this class. You're better at math than the math requires in this class. You're better at chemistry than the chemistry requires in this class. You're better at computer programming than the computer programming is required in this class. The new knowledge you are gaining here today is to translate real-world chemical engineering problems into thermodynamic calculations, basically. The material balance it's thermodynamics also. I hate to break it to you, right? Don't lose mass. First third of the class, don't lose mass. Second third of the class, is basically don't break the first and second laws of thermodynamics. Third exam in the class is don't violate the first law of thermodynamics. Questions? So we talked a lot about the heat of reaction, heat of formation method, so I don't necessarily want to go over that again, right? Because we've got about 12, 13 minutes left in class, so I want to hit any questions that we have. But hopefully this is a good overview. But remember, I'll get to the question in a second. Remember, on your exam, do not panic. Do not panic. Almost all of the questions will start off with energy balance. Now, there's maybe some intermediate steps where you do not have to do a state change. So for example, I think most all of them you have to do a state change. But there may be an intermediate where it says, what's the enthalpy of the outlet stream, for example. You wouldn't have to do a state change there. You could just apply the energy balance and you get an enthalpy, right? But to translate that enthalpy into a temperature and pressure, then you'd have to do a state change. So write out your energy balance for the problems. Is it an open system? Is it a closed system, right? Which form do I want to write the energy balance in? Then you have to do a state change. Now remember, when you write down your state changes, okay, the last big piece here, let me just do an intro on the reference state. Okay, I can only calculate delta H's. So delta H is H2 minus H1. But I can add in lots more steps into here, right? So I can go from H1 to H1A to H1B to H1C to H1D to H2. Does that kind of make sense? I can break it into multiple steps. But the overall delta H is going to be from 1 to 2. If I set this equal to 0, therefore, the enthalpy that I put into my balance is equal to the delta H's that I can calculate here, right? It could be a vaporization process, it could be a mixing process, it could be a reaction process, it could be a temperature change, it could be a pressure change. So you need to build a bridge from where you're starting to where you're going over data that you know has been measured. So if I have the heat capacity of one phase, I can use that. If I have the heat of vaporization at one state, I can walk through that state. If I know how much energy is released in a reaction, I will walk over the reaction at that temperature and pressure, right? But the goal here is to get a number for the enthalpy that I place into my energy balance using only delta H calculations. And that's why we start off at a reference state, and that means the delta H is equal to the H2. So we'll have to use a regular question back here.
Have you posted practice exam 3?
Yes, it was posted on Friday, I think. I think I sent an email actually too. I don't mean to call you out. Question.
So by convention, the enthalpy of state change is going from liquid, or whether it's solid to liquid, liquid to solid, it's H formation, right? Is that right?
No, so those are all just conventions. They're just made up terms, right? So heat capacity is made up. Nowhere in the universe as it tells that heat capacity has to be created like that. We created that. So the heat of vaporization, we made that up. So we call the heat of vaporization the energy that it takes to go from a liquid to a vapor. So that's H of vapor minus H of liquid. We thought that would be a useful unit to measure. We made it up. We defined the convention. On a parallel planet in a parallel dimension, they might define it as going from vapor to liquid, in which case all of theirs would be negative of all of ours. So if we have to melt something, going from a solid to a liquid, we look up the heat of fusion. Now, is it liquid to solid or solid to liquid? It's just a convention that we made up. I believe it's going from solid to liquid. So it's called heat of fusion, but it's actually like heat of melting. Right? Yes?
Will there be an exam review tomorrow?
Yes, I can do that. 2 o'clock is good? Or is 1 o'clock the one? 1's the one we always decide on. Okay, 1 o'clock. Yeah, we'll do exam review at 1 o'clock. I don't have much to add past this point, though, because the key thing is if you get the concepts, right? Start off with an energy balance. Please write your energy balance. Do your state change. So class, if you want, of course, you can leave at any point. You don't have to come to class at ever, right? But I'm here for 7 more minutes or so. Questions about the project, questions about the content, question here. What specifically about reference states?
Honestly, everything. I'm having a hard time wrapping my head around it.
Okay. So let's go over reference states again.
I think the biggest thing for everyone to use is just like using it in like the heat information like one of them like requires reference states.
Yeah.
And it's just like I can't recommend.
So let's talk about, okay, so let's go over quickly reference states for reacting systems, and let's just talk about how we can basically reconstruct everything. So heat of formation method, I need to get a series of delta H's together such that I can get an H2 that I will plug into my equation starting off at an H1 that I will call 0. If I wanted to, I could call my reference state 100. And what would that do? It would add 100 to all of the enthalpies in my system. And it would not change the Q, it would not change the work, it would not change anything. So 0 is a nice clean number, so I'm going to choose 0. So in the heat of formation, what is my reference state? What is my reference state in the heat of formation method? 25, okay, so reference state is 25 degrees C, 1 atmosphere. What phase of matter am I in, correct? Because I have to fully define the whole thing. What phase of matter am I in?
Liquid.
It could be liquid depending on the material, but it's at whatever phase it's going to be in here. Now, this is a reacting system, so what's the composition of my system here? It's the atomic species, right? So this would be O2, N2, carbon solid. It's going to be at whatever state these compounds happen to be in. Okay, so let's say I want to get to toluene. C7, 1, 2, 3, 4, 5, 6, 7, 8, H8, okay? And I want to know what is the enthalpy of toluene at 200 degrees C and 1 atmosphere pressure. I think I know the boiling point of toluene. Okay, that's my goal. So I need a number that I put into my table here. Okay? I need a number that I put into my table for that enthalpy. Oh, one last thing before we go over this. I forgot to mention this open steady state balance. So I know we've talked about like the energy balance of a reactor. We talked about the energy balance of like a piston cylinder, which is not that one. We talked about the energy balance of a flash calculation. What about the energy balance of planet Earth? Is that the same balance there?
No.
More or less, yes. Assuming that these are the forms of energy that we're keeping track of. What about the energy balance for an entire city? Same. What about the energy balance for an entire chemical plant?
That's only if it's at steady state, right?
Yes, only if it's at steady state. What about the energy balance of not 1 unit process, but 2 unit processes added together? Does this still hold true? What if I have 6 streams in and 10 streams out? Is that still true? It totally breaks it, right? Right? What if I know the details of the chemical process? Can I use this equation? What if I don't know the details of the chemical process on the inside, but I know what goes in and out? Yes, right? So this is not just for, this is one reactor. This is one flash calculation, right? This is one adiabatic mixer. No, we can lump as many processes together. We just draw a lasso around our system. We say that's the system, right? We don't have to know the physics of how the system operates. All we need to know is the inlet and outlet conditions for each of those different states. Does that make sense? Yeah.
Sorry, I know you're going on reference states. I just had a quick question.
Sure.
For the project, there's some volumetric flow rates that we have to derive from like a mole flow rate. Are we allowed to just use PV equals nRT to solve for that, or do we need?
If they're all gas phase, yes.
Okay.
If it's water, you'll want to look up the density of water at that particular state.
But we don't
But I
use
believe
St. Robinson or anything
No.
necessarily.
no. These are all pretty high temperatures, reasonable pressures. They're going to be pretty well described by the ideal gas law. I'm okay with that. Okay. So question?
I like the SCMA or whatever, the standard.
Standard cubic meter is not actually a unit of volume. It's a unit of moles. One standard cubic meter is 1 kilomole is 22.4 standard cubic meters. A standard cubic meter is not a volumetric measurement. It is a molar flow rate. It's the equivalent volume of 1 mole or kilomole at standard conditions, which is not 25 degrees C in one atmosphere. It's actually 0 C in one atmosphere. So a nice little wrench in the plans. Okay, so let's go back to our example. Toluene, 200 degrees C, 1 atmosphere. I'm starting at my reference state with solid carbon and gaseous hydrogen. Does that look like toluene to any of you?
No.
Does anyone know what toluene looks like?
Yeah.
What is the toluene structure?
Benzene with a little methyl group.
Benzene with a methyl group. Does this look like benzene with a methyl group? Do I have toluene at 200 degrees C in 1 atmosphere? So what's my first step? I have to do what?
Bring it down to
So I'm starting off at 25 degrees C in 1 atmosphere. I'm starting my journey there already. So I need to make toluene, okay? So then I do delta H formation at the standard state of toluene, and now I have created toluene, okay? Now I have toluene at 25 degrees C, 1 atmosphere, and should this be a liquid or a vapor? It's going to be a liquid unless I look up the heat of formation of gaseous toluene. But in this case, for the purposes of this example, for the reference state, we're going to use liquid. Okay, so now, is this at 200 degrees C in 1 atmosphere? So what do I need to do next? So I can do a couple of things. I have lots of options. I could vaporize it right now if I had the heat of vaporization at 25 degrees C. Then I could heat the gas up from 25 degrees C to 400. Let's assume I only have access to the heat of vaporization at the normal boiling point, which is 110. Okay, so 110 degrees Celsius is the normal boiling point for toluene. So what is my next step? I need to go and heat it up. So I'm going to go integral heat capacity of the liquid, integrating from 25 to 110 dT. So now I have toluene at 110 and 1 atmosphere saturated liquid.
And we do 110 because that's the boiling point.
That's where we have a measurement of the boiling point. But if we had a measurement of the boiling point at 25, I could directly vaporize it to 25 and then just heat it to 200. Right? So it depends on the data. You don't have to follow exactly this algorithm. Right? The world is your oyster. Right? If you find the data, use the data. Just build a bridge with data that you have access to. If I had the heat of formation of toluene in the gas phase, well, then just make it in the gas phase and heat it up. Sound fair? Okay, so now if I want to go from toluene as a saturated liquid to toluene as a saturated vapor, that would be the heat of vaporization plus delta H of vaporization at 110 degrees Celsius. Now I have saturated vapor toluene at 110 degrees C and 1 atmosphere. This is technically redundant information because the saturation pressure at 110 is 1. Final step, I need to get it to the right temperature, so then I just heat it up, plus integral from 110 to 200, heat capacity of vapor toluene dt, and I have reached my objective. Now, let's go back to where we began. I calculated a series of delta H's. In thermodynamics, I can only calculate deltas, delta P's, delta V's. Actually, no, I can do those ones. But delta U's and delta S's and delta H's, right? I don't know what the absolute value of the entropy of the universe is, but I don't care. I only care about how much it changes for the process that I want to accomplish. So everything that we're working at is du, ds, dh. When we integrate those, it goes to delta U, delta S, delta H. But because I started my journey at a really convenient location, my delta H is I created toluene, I heated the liquid, I vaporized the liquid, I heated the vapor. Okay? That is exactly equivalent to H2, the final state, minus H1, the initial state, because enthalpy is a state function. It doesn't matter the path that I choose. This is always going to be true. Delta H is always going to be equal to H2 minus H1. Since H1 is equal to 0, that means H2, the number that I put into my table, is going to be the summation of all of these delta calculations. Yes?
So I guess the biggest thing where I'm getting confused now is, so we're setting H1 equals 0, but I guess
You know what?
where's that?
Let's go back. You know what? Forget about this. I changed my mind. H1's actually 100. So you know what I'll do? I will just minus 100 from this side. Oh, actually, no, I'll plus 100 to this side, right? And then I'll just plus 100 to that side. And that's the enthalpy that I'll put in my table. Right? And every single calculation in my table now will have 100 extra joules of enthalpy, or 100 extra kilojoules of enthalpy, right? And it will not change the algebra whatsoever. So the 0 is just convenient, right? But the delta H, so forget about all this. The delta H is always H2 minus H1. So if I calculate a series of delta H's, it's always going to be equal to H2 minus H1. The enthalpy that I care about is the final state of either the inlet or the outlet conditions, right? So this could be 50 degrees C as a liquid. This could be 200 degrees C as a vapor. I could choose 50 degrees C as my starting point, but in this case, I started to make the molecule first. I would still have to make this molecule even if I'm only going to heat it up to 50 degrees C as a liquid, right? Because that step would cancel out on both sides. So it's technically more work, but conceptually it's pretty easy to understand. Right, so if you really wanted to, you could solve every equation in this class, every problem in this class by using the heat of formation approach, just knowing that nothing reacts and everything cancels out. Yes?
So basically everything but the plus 100 is our H2.
No, including the plus 100,
That's our H2.
right? Including the plus 100 is my H2. Because I chose my reference state to be having an energy of 100, right? But, so in this case here, instead of 100, I could write plus H1. Now let's think about calculus, right? So if I'm integrating dH, so we're going to get, this is like the constant of integration. It's the reference state. So when you're doing your calculus, you'll get, you'll integrate something and you'll get like the plus C at the end, right? This is the plus C at the end. But we can just set this equal to 0 to make our lives easier. But that's where this comes from if you want to kind of go back to a more calculus perspective. It's sort of like the constant of integration. Because we've integrated a dH to get a delta H plus a C for that constant of integration. We just set that constant of integration equal to 0. That's where that comes from. Okay. So unfortunately, we're out of time. I hope everyone feels prepared for the exam, but I will see you on tomorrow at 1 for some help hours, and then on Friday for the fun.